All right, Hassler here. I'm going to go through the 4-point notes on the antiderivatives and indefinite integrals. It does say student at the top because I had typed out my own for myself, but yeah, I'm going to work through this with you. Sorry, indefinite integrals, because we've been talking about definite integrals. And so I just want to take a minute to note that indefinite integrals are slightly different, and I'm going to define that down at the bottom. I did not have a typo. It's supposed to be indefinite. So I've been talking for the last couple of weeks about the fact that we're going to be going backwards. And so these first directions say find the original function using the given derivative. Okay, so first semester I gave you a function and you took the derivative, which represented a slope of a tangent line. And this time I'm going to give you that derivative, and your job is to go backwards and find the function. So we're going to talk about how to do that. In the past, I would have had you work with a neighbor to try to come up with some of these answers. I'm just going to go ahead and talk through how to do some of these. So if I have to find f of x, I have to go backwards, all right? And so what that means is I'm going to have to go from x to x squared, okay? Right, if I'm given an x squared function and I take the derivative, that brings me down a degree. But in this case, I want to go backwards. I'm given the derivative, and I want to go back to f of x. So I actually have to go up a degree. The other thing is I need to figure out what my coefficient should be so that when I do take the derivative, my exponent times a coefficient, I would end up with the 6 as my coefficient for the derivative. So I'm thinking to myself, okay, what times 2 gives me 6? That would be 3. Okay, same story, I have this 4. And I could really write this as 4x to the 0, right? If there's no variable, then the exponent on the variable would be a 0. So again, and I have this plus in between. So again, I would need to up the exponent if I'm headed backwards, right? When we take a derivative, we subtract from the exponent, but I'm going backwards. I have the derivative, and I want to go backwards, so I'm going to add to the exponent. It's going to give me x to the first. And again, I have to think about, okay, if I have a degree of 1, what would I multiply that by if I were taking the derivative to get this 4? Well, I would have to multiply by 4. The other thing to consider, and we're going to talk more about this, is I could have had a constant, right? Like this function could read as 3x squared plus 4x minus 10. And when I go to take the derivative, minus 10 would have a derivative of 0. Notice that there's nothing written. I'm going to do this in red so you can see it better. There's nothing written past the plus 4 in my derivative function because the derivative of any constant is 0. And so what I'm going to say is, well, I could make this a minus 10, right? You could pick your favorite number. 10 is not even my favorite number. Why am I even picking 10? 12 is my favorite number. But I hope you get the idea. And then I say, well, you can always check your solution by taking the derivative, right? So I can check my solution and say, well, if I were to take the derivative of f, okay, then I would have f prime of x. And if I take the derivative, 2 times 3 is 6. Subtract 1 from the exponent. 1 times 4 is 4. Subtract 1 from the exponent. And the derivative of a constant is 0. So it matches. Okay, so it's kind of like this self-check. Whatever you come up with, you can take the derivative of and see if you land with the given. Okay, and so it's really the same process throughout. It's this idea that if I'm given a derivative, I'm going to come up with the original. Okay, so same idea. I'm going to add 1 to that exponent. And then I have to think, what would I have to multiply my exponent by to get negative 3? Well, I'd have to multiply by a negative 1, okay? Minus, again, same thing here. I'm going to up my exponent. And what would I have to multiply 2 by to get negative 4? Well, I'd have to multiply by negative 2. And then again, I can put whatever my favorite constant is. And this time I'm going to put plus 12 because 12 is my favorite number. And I can always check this by taking the derivative, right? And if I take the derivative and I multiply the exponent by the coefficient, I get negative 3x squared. I get a minus 4x, and the derivative of 12 is 0, so it matches. And I hope that you're starting to maybe see some patterns or some ideas that we can apply as we move on. Okay, I'm running out of space here. Okay, so I'm going to go ahead and pause for a minute to see if you can try number 3, and maybe we can come up with the same thing. Okay, so let's see if you came up with what I came up with. I came up with the original function would be 1/5 x to the 5th minus 3x cubed. I had a plus 1/6 x squared, and I had a minus 2x, and then I'll just call it a plus 4, whatever your constant is, okay? And I can always go back and check, right? I can go back and check, and I can say, well, did I do this right? I hope so, right? If I do 5 times 1/5, I get this coefficient of 1. Subtract 1 from the exponent. 3 times -3, I get the coefficient of -9. Subtract 1 from the exponent. This was the tricky one. 2 times 1/6 is 1/3. Subtract 1 from the exponent. 1 times 2 is -2, and then whatever my constant is. Okay, so there has to be a rule that goes with this, and there is a rule that goes with this. So we're going to write what that general rule is. This is write a general rule to show how to obtain the function f of x given f prime of x. So I'm just going to say if f prime of x is equal to a x to the n, then to go backwards and get the regular function f of x, okay, I'm adding 1 to the exponent, so n plus 1. Right when I take a derivative, I subtract 1. Now I'm going backwards. I'm going to add 1. And how I deal with the coefficient is I say, okay, I'm going to take that coefficient and I'm going to divide it by the new exponent. So we're going to go ahead and test this rule, okay? So if I have y prime equals 3x to the 4th plus 2x to the half. Yeah, I know, I threw a fraction in there, okay? Then based on my rule, y would be equal to 3x to that. I'm going to add 1 to the exponent, and I'm going to divide by that new exponent, okay? Same story here. So I have plus 2x to the 1/2. I'm going to add 1 to the exponent, and I'm going to divide by the new exponent. And then what I'm going to do is I'm just going to say plus c. So, up at the top, we had been talking about this, this plus 4, or I did, I did have a 12 in here. I don't know what happened to it. And down here, plus 4. Okay. That's what happened. I'm not looking at the right spot. My apologies. There we go. I had a minus 10. That's what I had. I just came up with my own constants. Minus 10, a plus 12, a plus 4. Okay, so instead of making up your own constant, because all of our constants are going to be different, we can just say plus c to say, well, I could pick any number, really. Okay. And so if I were to simplify this, I would get 3/5 x to the 5th plus, all right, half plus 1 is 3/2, and so I'm doing 2 divided by 3/2. When I do that, I get 4/3. Okay, x to the, again, half plus 1 is 3/2. And I'm just going to say plus c because I could put any constant in there. And then again, I could always take the derivative to check that I end up with 3x to the 4th plus 2x to the half, okay? Okay, so some definitions. The definition of an antiderivative. Well, An antiderivative is literally the opposite of a derivative, okay? So antiderivative, and I'm just going to say this undoes a derivative. That's literally what we just did at the top. I gave you a derivative and we undid it. It's like the inverse of a derivative, okay? Antiderivative. Okay, so a function capital F of x, here's where notation is going to get bogus on us. A function capital F of x is an antiderivative. This is a big deal, okay, of little f of x. So capital F of x is the antiderivative of little f of x on an interval. And if I take the derivative of capital F of x, I get little f of x. And here's what that's saying, okay? That's saying back up here that this function that we found, this was the antiderivative. Okay, this is the antiderivative. So you were given a derivative, y prime, and we found the antiderivative. That's called capital F of x. And if I were to check this, if I were to take the derivative of this capital F function, right, that was my check, I would get 3x to the fourth plus 2x to the half, okay? And that we call little f of x. All right, so that's all that's saying. They're just giving the antiderivative a name, capital F of x. And this says, and this notation gets a little hairy, that's why I'm going over it. This says if I take the derivative, come on. There we go. Of this capital F of x, I'm going to undo that antiderivative. I'm going to be left with what I started. All right, and I hope that that kind of settles in a little bit the more that we do. Okay, so it's this example. If little f of x is equal to 10x plus 9, then capital F of x is 5x squared plus 9x. Okay, so if you take the derivative of capital F of x, in other words, if I take the derivative of capital F of x, I would get 10x plus 9. And that matches little f of x. That's all that's saying, okay? Okay, so example, find the antiderivative of little f of x. And the reason why they use this notation is instead of saying find the antiderivative of f prime, and that leaves you with f, you're going to be given functions f, and you're going to be asked to find the derivative and the antiderivative. And so the notation can get a little hairy, okay? So when we say find the antiderivative, we call that antiderivative f of x, okay? So if I want to find the antiderivative of this f function, I'm going to call that f of x, and that's where I do the whole, I'm going to add 1 to the exponent and divide by my new exponent and add c. And when I do that, I get 12 over 8, right? 12 over 8 is 3 over 2, x to the 8, and then this plus c. All right, so the general antiderivative, let capital F of x be an antiderivative. Got it. That's like the third time I've said this on the paper. Of little f of x, then every other antiderivative is of the form capital F of x plus c for some constant c. That's just saying don't forget to add c, because when I go to take the derivative of that function, the derivative of c is 0. That's what at the top, you can pick whatever c you want. So we just say c for everyone in general. All right, so indefinite integral, and that's what I had set up at the top, an indefinite integral. And an indefinite integral looks like this, all right? If I find the antiderivative of little f of x, so this says find antiderivative of little f of x, that's equal to capital F of x plus c. And notice that it's called indefinite because there are no limits of integration. So we've talked about a definite integral, and a definite integral has limits, a to b, whereas an indefinite integral does not. All right, I'm going to pause and then go over the backside in a different video.